Colloquium speaker. Scott has made major contributions to several fields of astrophysical dynamics, all the way from planetary dynamics through stellar systems, black holes, and galactic dynamics. If you don't know his book with Binet, it's a very thick book, Galactic Dynamics, which is widely used. In terms of planetary dynamics, he predicted with Goldreich the existence of Shepard satellites and density waves in Saturn's rings. He works on planetary migration. He also was part of a group that showed that almost every galaxy contains a supermassive black hole as the center, and studied the relation between the mass of the black hole and the dynamics of the galaxies. Recently, he's been working on axon-like particles in cosmology. I don't think I'm going to talk about this. Scott is currently a professor at the IAS, and before this was chair of the Astrophysical Science Department at Princeton University, and previous to that was the first director of the Canadian Institute of Theoretical Astrophysics. He has numerous prizes, including the Dick Brower Award, Danny Heinemann Prize, and I'm going to stop here. So, yeah, I'll let you tell us about.
I'm going to try to talk about three topics here, since not everybody here works on comets. I'm going to start with a review of what you might call the standard model of comets. This is a subject where I think we really do understand remarkably well what's going on in fragmentary data. I'll then talk about discussions of a hypothetical planet 9 in the outer solar system, where we may sort of understand what's going on, but not completely.
Is that a good idea?
Yes.
Yeah.
And finally, I'll talk at the end about ʻOumuamua, the first interstellar asteroid, where I have absolutely no idea what's going on. So for the purposes of this talk, you can think of comets as pieces of ice and rock, typically a few kilometers in size. They're rubble piles, that is, they're porous, so they have densities that are quite low, typical masses, a few times 10 to the 16th grams. They're believed to be leftover small bodies, which I'll call planetesimals, that were the original building blocks of the solid components of the planets, and which were kind of left behind because the workshop for building the planets wasn't cleaned up completely. We've had spacecraft visit half a dozen of these things, with images shown here. The comets are typically visible because as the comet approaches the sun, the volatiles in the cometary nucleus, those chunks that you saw earlier, evaporate. There's dust, which is visible by reflected sunlight and produces a tail whose shape is determined by radiation pressure and solar gravity. And then there's a plasma tail determined by its interactions with the solar wind. And in some comets, such as this one, you can see the two tails quite distinctly.
When you say rubble piles, does it also mean that the objects don't have, I don't know how to say it, can't spin faster than breakup?
Yes, so that's clearer with asteroids. When you look at asteroids above a particular size, there's an extremely sharp cutoff in the distribution of rotation speed.
So meaning they really are just gravitationally held together piles of rock.
Yes.
And at some point, you're going to remind us of the distinction between comets and asteroids.
No. Well, yeah, maybe I will. I will later. For now, don't worry about it. Okay, so because the tails only become visible when volatiles come off, if the comet is at large distances, all you have is the inert nucleus. That means they're visible only by reflected sunlight. They have a low albedo, and because it's reflected sunlight, there's a 1 over r squared law for the light going to the comet, 1 over r squared for the light coming back. Their brightness falls off as 1 over r to the 4th. And that means that it's extremely hard to discover comets beyond a few astronomical units. That means there's an extremely strong selection effect on the comets that we've discovered, which I'll try to, and much of what I'll say is trying to extrapolate from that to the total population. Once a comet comes close enough to the sun, on the other hand, because it's evaporating, it can rarely survive more than a few hundred orbits. And since a few hundred orbits is much less than the age of the solar system, there has to be a reservoir of comets somewhere, which satisfies two criteria. It has to be sufficiently stable to store the comets for something like the lifetime of the solar system, a few gigayears. On the other hand, it can't be too stable. It has to be leaky enough that there's a steady stream of comets coming into the inner solar system where we can see them and where they'll eventually be destroyed by evaporation from solar radiation. So to try to study where these reservoirs are, you have to use the known orbits of the comets. And just to briefly review freshman mechanics, all the orbits are ellipses and point mass potential. They have a semimajor axis and eccentricity. They have a point of closest approach to the sun, the perihelion. They have an inclination, which I'll always measure relative to the plane of the planets. And they have an orbital period. And Kepler's law for the solar system says the square of the period in years is the cube of the semimajor axis in astronomical units. The energy per unit mass in Kepler orbit is minus gm over 2a, and the convention in this field is to set g equal to unity, m to unity, 2 to unity, and minus 1 to unity. And so I'll call the energy 1 over the semimajor axis. Similarly, the angular momentum has an expression like this. Most of the comet orbits are highly eccentric. That means the eccentricities near unity, so you can approximate 1 plus the eccentricity for many purposes as 2, and that just says that the angular momentum goes like the square root of the perihelion distance. So this is a plot of the comets that we know of with reasonably good orbits, discovered from a very heterogeneous set of sources. I plotted the period along here, and the perihelion distance along here. Of course, there are selection effects. The first that I already mentioned is that it's very hard to see comets that don't come close to the sun. So perihelion distances bigger than about 2 astronomical units are seriously underrepresented. If the comet has a very long period, the chance that it will come through perihelion during the time when we've had reasonable telescopes is lowered. So once the period's longer than a couple of hundred years, the comets in this region are also seriously underrepresented. And finally, it's very difficult to distinguish nearly parabolic orbit from a parabolic one. And so what tends to happen is everything that's close to parabolic is either assigned parabolic orbit or just assigned a fixed period. Here I've just assigned them all to a period of 10 to the 6 years. So this line is an artifact. The first feature of this that you kind of like to understand is this ridge here. That's actually pretty easy to understand. If you use the period and the perihelion distance, you can make a plot of the locus for which the aphelion of the comet, the point of furthest approach, is equal to Jupiter's orbital radius. It lies right along this ridge, and the way to think of that arising is that when comets enter the region of the giant planets, they undergo a sort of pinball where they ricochet between the planets. A large fraction of the ones that we see had a close encounter with Jupiter, which flipped back from being the perihelion to the aphelion. The perihelion became much smaller. It came close enough that we could see them, and so a lot of them are left in the condition of their aphelion is close to Jupiter's orbital radius from the last close encounter.
And is the next ridge you can see there, is that Neptune? Do I see another ridge?
I don't see it. You're better with big data
I'm
than
an
I am.
astronomer, so I see the ridge.
This is making me nervous. Okay.
It kind of goes through 100 periods in one AU. Is the lower left of it?
I'm sorry?
I mean, look at it, it's obvious.
100 years, one AU is the bottom left of the ridge you see?
No,
Uh-oh.
I see a ridge right here.
Oh.
Let me keep going. Okay, this is because the comets on that ridge are so clearly affected by Jupiter, the standard classification is to say that everything with a period less than about 20 years is called a Jupiter family comet. This region from 2200 is called a Halley family comet because the famous Halley's comet is here, and long period comets are everything longer than about 200 years. The other useful plot is to replace the perihelion distance with the inclination. So this is inclination from 0 to 180 degrees. Halley's comet has a large inclination, so it's now moved up here. And the central thing you see here is that the Jupiter family comets with periods less than about 20 years all have quite low inclinations relative to the plane of the planets, to the plane of the ecliptic, whereas all the ones with long periods are essentially isotropic. What that means, since there's no way with dissipationless celestial mechanics that you can convert a spherical distribution into a flat one, the Jupiter family comets have to come from some sort of reservoir that's a flat disk aligned with the planetary system. That recognition dates back to a couple of papers from the 1980s, and it was confirmed in the 1990s with the discovery of what's now called the Kuiper Belt, a large collection of icy bodies starting roughly at Neptune's radius and extending out to about twice that distance. We now know of, this was the discovery image of the first one, but we now know of something like 2,000 Kuiper Belt objects. The Large Synoptic Survey Telescope is estimated to discover another 40,000. We believe that the Kuiper Belt is the source for almost all of these comets. It has a total mass of about 1/10 of an Earth mass. As I said, as a reservoir, it has to survive for gigayear timescales. That's simply because most of the orbits out there are stable on those timescales, but it also has to leak, and the leakage mechanism are probably a combination of rare collisions between comets that change their orbits and allow them to come into the region of the planets where they, again, start to undergo this pinball process, or possibly very weak chaos in some fraction of the phase space in the Kuiper Belt. The problem I'll spend more time on is the origin of this isotropic population of comets at longer periods. In order to talk about that, as I indicated, rather than the orbital period, which goes off to infinity at large distances, I'll use the energy or the inverse semimajor axis and simply replot this diagram with inverse semimajor axis here instead of orbital period. When you do that, you see something that looks like this. There's again the inclination, the inverse semimajor axis in units of inverse astronomical units. There's Jupiter at about 5 astronomical units. There are the Jupiter family comets at low inclinations. And then there's this compressed cloud of points at higher inclinations out here. So to see what's going on, you just expand the scale. I've expanded it by a factor of 10. It's still relatively featureless, except that the Jupiter family comets have disappeared off the scale. Expand another factor of 10, it's still pretty much featureless. Expand another factor of 10, and it's still pretty much featureless. Now, you can do better than this. You can sharpen the plot by recognizing that all of the comets that we see at, of course, at small perihelion distance. That means they've already passed through past the giant planets during their inward orbit. And roughly speaking, if you have a planet with some mass at some semimajor axis, it'll impart a typical energy and a change in the inverse semimajor axis that's roughly the ratio of the planet mass to the solar mass times 1 over the planet's energy per unit mass. And that means that the energies that have been plotted here have been contaminated by the the planets. And so the appropriate way to sharpen the plot is to do a numerical orbit integration for each comet, which takes it back through the planetary system out to a distance of maybe 50 or 100 astronomical units to a point before it entered the planetary system, so you can figure out what its original semi-major axis was. When you do that, the plot looks like this. So again, this is 1 over semi-major axis. The plot has been expanded, so it's on the scale, same scale as the last plot I showed a couple of slides ago. So this is an inverse semi-major axis of 10 to the minus 4 in astronomical units. The corresponding semi-major axes here is about 10,000, and at energy of 0 is a parabolic orbit.
And you're saying that we can observe the six space position and velocity of these comets so precisely that you can run back through the solar system and
Sure.
run back the perturbations and bring them back to what
Well,
they
you're
were
only
before.
running them back through one passage,
perturbation,
so
one
it's
close,
it's
and
not so bad.
everyone does indeed have a closed passage. Like it all works out.
Well, I don't know what it, it all works out. There are the original inverse semi-major axes. Okay. So the first thing you'll see about this is that some fraction of the comets have negative semi-major axes, which means that they're unbound. But in fact, if you look carefully at the ones that are apparently hyperbolic, those are ones with relatively large observational errors, or they have some evidence of non-gravitational forces from outgassing from the planets. So it's generally assumed, and I think is a pretty good assumption, that every comet that you see in this region started off in a bound orbit, an orbit with positive semi-major axis or negative energy. Now, this is actually pretty remarkable. As David pointed out, these are very small energies, and one way to illustrate how small these energies are is, let's just imagine for a moment that gravity is not an inverse square law, but described by ʻOumuamua potential. So there's an extra factor of e to the minus m times the radius. What that does is it weakens the gravitational potential from the sun at large distances, and that means that orbits that you thought were bound if the force law was Newtonian are not bound anymore. Now, since you see this huge spike here, it would be implausible if all of those were unbound orbits. And so if you just say, well, the escape energy has to be closer to 0 than, say, 100 here, you get a constraint on the range of the ʻOumuamua potential. If you translate that into a mass of the graviton, you get a limit of 10 to the minus 23 electron volts. Now, for comparison, the limit that came from LIGO, from the lack of dispersion in gravitational waves, from the black hole merger, is about 3 times worse, about 10 to the minus 22 electron volts. I'm not really seriously arguing that this is the best limit we have on the graviton, although I might be graviton mass, although maybe I could do that after a few beers. But I just wanted to stress how remarkable it is that this peak comes out so close to 0. And what it tells you, of course, in the context of Newtonian gravity, is that the reservoir for this isotropic set of comets must be bound to the solar system and at extremely large distances, at distances of order 40,000 times the Earth's sun distance. This argument was originally made by Oort, and so the reservoir has come to be called the Oort cloud. And I just wanted to stress, particularly since David is in the audience, that the original paper from Oort reached this conclusion from a sample that looked like this. He had 10 comets in this peak and about another 10 comets outside it. And the conclusion to reach from this, of course, is that you don't always need big data to reach an important conclusion.
Actually, it's even worse than that, right? Because very few physical properties of the Oort cloud have changed since Oort, right?
Yes, that's correct.
He basically nailed it.
Right. Okay, so the other thing you can notice from this is, remember I said that comets typically got a random energy perturbation when they pass through the planetary system. That means each time a comet from the Oort cloud comes through the planetary system so that we can see it, it gets an RMS kick on this scale of about 10 to the minus 3 inverse astronomical units. That means that the evolution of a comet that came through the first time from this spike is basically just a standard Gambler's ruin problem. It gets a random kick which can either be positive or negative. If it's positive, on the next passage the comet is somewhere over here. If it's negative, it escapes. So that means that the fraction of these comets that survive in orbits is the same as you get from Gambler's ruin or first passage time in random walk. It's the number that survive for more than n orbits goes like n to the minus a half. And this relatively flat distribution of comets out here is basically what you would expect from the steady state solution of the appropriate Gambler's ruin problem. You can do more, and again, this is stuff that Oort did. The rate of arrival of new comets from the Oort cloud with a perihelion inside the Earth's orbit is about 4 per year. The orbital period at the distance of the Oort cloud is about 30,000 astronomical units, is about 5 million years. The leakiness in the Oort cloud arises because of it's constantly being randomized, its orbits are being randomized by kicks from passing stars and torques from the galactic tide. And those are sufficiently strong that you should think of it as something like a microcanonical ensemble. That is, there's an energy surface at constant semimajor axis, and these randomizing kicks fill the energy surface in phase space uniformly. Well, we know that the fraction of phase space on a given energy surface at a given semimajor axis with perihelion less than some value is just 2q over a from the geometry of Keplerian phase space. And that says that the fraction of comets on this energy surface that pass close enough to the sun to come inside 1 astronomical unit is just the ratio of these numbers. Then you can immediately calculate the total number of comets in the Oort cloud. It's the rate, 4 per year, times the period, 5 megayears, times the fraction of phase space occupied by comets that come within 1 astronomical unit. Putting in those numbers, you get about 3 times 10 to the 11th comets. I gave you a typical comet mass of a few times 10 to the 16 grams. Together with the number of comets, this gives an estimate of about 3 Earth masses for the mass in the Oort cloud.
Scott, there are probably members of the audience who don't know what an AU is in some unit, like the distance to the nearest star. So people might like to know.
My apologies. Yes. So the AU is the.
I'm sure they know what it is.
The distance to the nearest star is about 200,000 astronomical units. So the astronomical unit is Earth-Sun distance. It's about 200,000 to Alpha Centauri. So the distance of the Oort cloud is about 10% of the distance to the nearest star. Thank you.
The thing I don't love about this argument, and maybe it's off topic, is that it feels like the kicks from nearby stars would coherently affect many Oort cloud members because there's not tons of kicks in 5 megayears. There's a small number of kicks in 5 megayears. So wouldn't we see some like coherence to the input of comets?
In principle, yes. That is, in principle, the directions of the comets that you see might exhibit correlations. The problem is that there's nothing like the Sloan survey for comets. Mm-hmm. Many of these are discovered by amateurs or by surveys of very limited areas, and so it's very hard to make a reasonable estimate of the actual unbiased distribution of comet orbits. With LSST, this should be better. There's some chance LSST would see asymmetries that you could trace back to individual stellar encounters. So I'd just like to stress once again that Oort's original sample of comets was about 10. So this estimate is an extrapolation by a factor of about 10 to the 10th, but is still believed to be accurate within a factor of a few. Okay, well, you can still do more. This is a description of the Oort cloud as it now exists, but you can ask how the Oort cloud was formed. In this case, there is a standard model. It assumes that the planets formed in their current orbits, that the galactic environment was the same as it is now, and that after the planets formed, there was a distribution of small bodies, planetesimals or comets, on nearly circular coplanar orbits, fairly uniformly distributed between the planets. And then gravitational kicks from the planets gradually excited the eccentricities and inclinations of these small bodies that in the inner solar system, the generic outcome of that is that the small bodies collide with the terrestrial planets. In the outer solar system, because the planets are more massive and the escape speeds are smaller, rather than colliding with the planets, they tend to have near misses, which excite the eccentricities still further. They gradually random walk to very high eccentricities and large semi-major axes until, in the inverse of the effect I talked about before, kicks from the galactic tide and passing stars increase the angular momentum enough that they no longer come within the planetary system and they're frozen in place in the Oort cloud. Now the nice feature of this model is that everything in it can be calculated once you give it a plausible set of conditions, initial conditions, and it only requires n-body integrations. This is an example of the kind of simulation that people have carried out. This is the perihelion distance versus semi-major axis. For the initial distant planetesimals, they're color-coded by the initial radius, and then shown at a series of time intervals ending up at roughly the current age of the solar system. And you can see that as time goes on, the kicks from the giant planets tend to increase the eccentricities, but keep the perihelion distance the same because they have to keep coming back to encounter the planets, until eventually, when the semi-major axis gets large enough, torques from passing stars and the galactic tide increase the perihelion distance and freeze the comets in place, until finally, after 4 gigayears, you have a distribution of comets centered on around 30,000 astronomical units, exactly where the Oort cloud is seen, with a wide range of perihelion distance. Most of the circles you see here are red and green. That means that most of the comets came from this region. That's somewhere between Uranus and Neptune. Comets that start off close to Jupiter get much larger kicks and just tend to be ejected. You can also look at the inclinations. This is a similar plot. Since it's inclinations here, they all start off at 0 relative to the planets, and you can see that after 4 gigayears, you have a roughly isotropic or spherical Oort cloud with a wide range of inclinations, and that everything beyond the semi-major axis of around 5,000 astronomical units has been subject to enough kicks that it's essentially isotropized and covers the energy surface uniformly. The process is somewhat inefficient. This is the fraction of the initial planetesimals that are left in the Kuiper belt in the region outside Neptune, in the outer Oort cloud outside 20,000 astronomical units. In the inner cloud and the total cloud, you can see that the population maximized at around a gigayear, at about 20% of our current age, and has now been gradually declining and eventually will all be lost. The efficiency is about 2.5%. That is, at present, a couple of percent of the initial planetesimal population is still residing in the outer Oort cloud at the current time. And we know roughly what the mass in the leftover planetesimals should have been when the solar system was formed. We can multiply that by 2.5%. You get a mass of the outer Oort cloud around an Earth mass. You can remember that Oort's original estimate gave a mass of around 3 Earth masses. So within what I think is a very reasonable factor given the uncertainties, the standard model predicts all of the properties of the Oort cloud: size, orbital distribution, and total mass. So I think this is a huge success story, but like with the other standard model, there are problems. I'm going to focus on one problem in particular. It's the problem caused by this little body. Sedna is an object with an orbit that looks like this. It orbits well outside Pluto. It's about 500 kilometers in radius. Its aphelion is almost 1,000 astronomical units, and its perihelion is 76. For comparison, Neptune is the outermost major planet in the solar system, and it's at 30 astronomical units. That means that Sedna's perihelion is so large that it feels almost no kicks from the planets. That means that if you integrate its orbit forward or back for 5 billion years, it stays almost the same. Sedna is not isolated. In the intervening 15 years, about 30 other objects with similar orbits have been discovered. They're now called the detached disk, in the sense that they're detached from the giant planets. And of course, the problem with Sedna in these objects is they don't fit in the standard model. If you can integrate them forward or backward in time for the lifetime of the solar system, and the orbits don't change, then how did they get there? We don't believe that it would be plausible for them to form in their current orbits. The whole basis of the standard model for the Oort cloud is that everything started in a planetesimal disk near the planets and got ejected, and that model fails for Sedna. I'd like to describe one possible explanation for this anomaly. The models I've described you are based on the idea that you have a population of 2 particles. You have the planets and you have a bunch of test particles. That division is artificial and oversimplified. It's far more likely that the planet formation process would produce solid bodies with a continuous distribution of masses. Jupiter, Saturn, and the other giant planets are believed to have solid masses in their cores of about 10 Earth masses. So it seems highly plausible if there's a continuous distribution that in the process of forming these 10 Earth mass cores, you also made at least a few Earth mass bodies and probably many more bodies of about Mars mass, of about 1/10 the Earth mass at the same time. From the point of view of a gravitational encounter, all that matters is that these, like the comets, are much less massive than the planets. And so if you eject comets into the Oort cloud with an efficiency of a few percent, you're also going to eject these into the Oort cloud with an efficiency of a few percent. And so it's likely, given the efficiencies, that there's probably 1 or more bodies that could be as large as Mars or maybe even Earth in the Oort cloud. The second effect is more relevant to Sedna. As these bodies are in the process of random walking out to the Oort cloud, there'll be one of them might be in an orbit like this. Because it has a non-zero mass, it exerts a torque on all the other comets that are random walking out to the Oort cloud. That torque will change the angular momentum of the comets and can raise the perihelion distance enough so that they no longer feel the influence of the giant planets, and they become frozen in place, and that they might have orbits that are similar to Sedna's. Trying to figure out whether this was true was part of the thesis of Kedron Silsbee at Princeton. He did a large number of simulations where he followed the 4 giant planets, a large number of test particles, and a few dozen extra bodies of masses on either side of an Earth mass. And for a broad range of parameters for these masses, he found that at the end of 5 billion years, there was a large population of the test particles left surviving in orbits like this, with perihelion outside Neptune at 30 astronomical units, ranging out to about almost 100, with inclinations of a few tens of degrees. Both of these parameters, the distribution of perihelion distances and inclinations, are very similar to those of the limited number of bodies we have in the detached disk. And so I think this provides a very plausible mechanism for producing bodies like Sedna and the other bodies in the detached disk, consistent with the standard model for the Oort cloud. What's also interesting is that in a significant fraction of the simulations, one or maybe two of those massive bodies, the bodies of masses around an Earth mass, also got locked in the detached disk. And that says that it's likely, but not certain, that the solar system contains an undiscovered planet around Mars mass or Earth mass of the semimajor axis less than a few hundred astronomical units.
So can I ask a question? Because I got a little bit lost. The argument is that the Oort cloud, you random walk your way out there, but the detached disk, these things can't have random walked their way out because. But then you just said that these things formed in the same way that the Oort cloud formed. So what's the difference that let them random walk their way?
If all you have is test particles in the giant planets, everything will random walk out of the Oort cloud to escape. If you have some massive bodies, most of them will go out to the Oort cloud, but a fraction of them will get frozen in place much earlier because of these torques from the massive bodies.
Okay, so it's the fact that there are some large things in there.
There are some large things. They freeze some of them at smaller semi-major axes and freeze them out of the random walk early.
But how do the large things then random walk their way out there?
Because the large things are still subject to perturbations from the giant planets. The giant planets don't care whether, the giant planet Jupiter has a mass of 300 Earth masses. It doesn't care whether it's perturbing something that's 1 Earth mass or 10 to the 16 grams. So most of them random walk out in exactly the same way as the comets.
Right. Sorry, but there's like a time reversal argument here, right? That if it's out there and never comes closer than 30 AU, then it couldn't have random walked its way out to somewhere where it never gets closer than 30 AU, right?
That's correct. So the time asymmetry arises because some of these things, there's a planet out here in a process of random walking out. It changes the perihelion of something so that it's frozen in place. Before that comes back into the planetary system, the massive body continues to random walk out and is lost. And so then there's nothing left to torque the body like Sedna, and it just sits there. Thank you. Okay, so this is a prediction of a Planet 9. Unfortunately, there's so many Planet 9 predictions that you can't tell them apart without a scorecard. And so I just have to tell you about the alternative, the other prediction of Planet 9, which arose from a completely different argument. If you look at a selected sample of Kuiper belt objects with large semi-major axes, you find that they exhibit an unexpected correlation in a couple of the orbital elements. The simplest one to understand is what's called the longitude of perihelion, which is just the azimuthal angle, the point of closest approach to the sun. This small sample of 7 or 8 of these bodies shows that the distribution of long axes is all biased towards 1/2 of the range of possible azimuthal angles from 0 to 2 pi. This concentration can't be primordial because the precession rate of these orbits is sufficiently large that they would randomize in much less than the lifetime of the solar system. But Brown and Batigan at Caltech have argued that this concentration, first of all, that it's real, that it's not an observational selection effect, that it's statistically significant, even though there's a relatively small number of objects, and that it can be caused by the dynamical effects from a planet whose mass is around 10 Earth masses semimajor axes of 500 to 1,000 astronomical units. So the scorecard for Planet 9, the original Planet 9, of course, was supposed to be a body that caused unexplained anomalies in the orbits of the known outer planets of Uranus and Neptune. That argument was made 100 years ago. It led to the discovery of Pluto in 1930, but it's now known that Pluto's mass is too small by a factor of something like 1,000 to produce the anomalies that led to the search. So the success of the search was basically a coincidence. It's more the anomalies are still there, but it's now more likely that they were due to the use of an incorrect Neptune mass. The Neptune mass got much better when the Voyager spacecraft flew by, and they discovered that the old mass was off by 0.5%, and if you correct that, most of the anomalies go away. So that particular Planet 9 is not doing so well. Fatigan and Brown's argument is that there's a Planet 9 that creates asymmetries in the directions of this selected sample of Kuiper belt objects. I've argued that there are plausibly a Planet 9 that was ejected into the Oort cloud along with the along with the comets. It would be a distance of about 10,000 astronomical units, and Silsbee has predicted that there might be a massive body with a mass somewhat less than an Earth mass at a smaller distance, and that this would be a member of the detached disk and one of the contributing causes of the formation of the detached disk. So can we see any of these? Is there any direct evidence for any of these things? Well, if you were thinking of a Planet 9 that was a giant planet like Jupiter, those are self-luminous in the infrared. They're still gravitationally contracting. That means the flux only falls off like distance squared, so they're visible at relatively large distances. But the WISE, Wide Field Infrared Survey Explorer, did an all-sky infrared survey and was able to rule out any analog of Jupiter within about 80,000 astronomical units. So there's no Jupiter in the Oort cloud, and there's no Jupiter out to 30% of the way to the next nearest star. If you have a much smaller planet, a terrestrial planet, those are much harder to find because they're visible only in reflected light. As I said earlier, that means the flux goes like the distance to the -4th power. What's equally bad is that not only is it getting fainter, but the number of background stars is going up, like flux to the 3/2. So if you want to go to a factor of 2 greater distance in your survey, you're going to have a factor of 30 more background stars to distinguish from. There are a couple of surveys that go to brightnesses similar to Sedna and cover, well, the biggest one is 12,000 square degrees compared to 40,000 sun in the whole sky. So they're certainly not complete. There are also dynamical constraints. You can add Planet 9 to a solar system ephemeris and see how big a Planet 9 you can put in. There's constraints from pulsar timing, the same pulsar timing that's used to detect gravitational waves. You would see a signal if the barycenter of the known solar system was accelerating towards some unseen object in the distant solar system. A possible future way to look for these things is gravitational lensing. The Gaia astrometric satellite that was launched a couple of years ago by the European Space Agency has sufficiently precise predictions of sufficiently precise measurements of the positions of stars that as Planet 9 travels through its orbit, its gravitational lensing would create systematic shifts in the positions of the stars as measured by Gaia that could be detected if you fit for them properly in the Gaia catalog. Roughly speaking, the parameter space looks like this. If this is distance going out to the tidal limit of the sun, and mass and Earth masses from a variety of measurements, pulsar timing, ephemerides, you can exclude a region like this. Gaia will potentially exclude an additional region here. For comparison, known Kuiper belt objects are here. The prediction from Batygin and Brown is here. Prediction from Silsbee is roughly here. So the objects that are being predicted theoretically are not far away from the limits that are available now or in the near future, and there's some reason to be optimistic that if the predicted planets are out there, we should be able to find them. Okay, finally, let me switch topics and talk about ʻOumuamua. This is a remarkable object which was discovered a little over a year ago by the Pan-STARRS survey in Hawaii. Its orbit looks like this. The thing that's remarkable about its orbit is that it has an orbital eccentricity of 1.2 with a fractional accuracy better than 10 to the minus 3. That means it's hyperbolic, not bound to the solar system. It means it's the first body we've detected that's come through the solar system from interstellar space other than dust. The properties are puzzling. It's a point source. You can't resolve it. It has no evidence of a tail, no evidence of a coma, no evidence of gas being released from it. All of those are inconsistent with a standard comet made of ice, but imply that it's made of rock rather than ice. So to answer Glennis, if it's made of ice, it's a comet. If it's made of rock, it's an asteroid, for the purposes of this talk. The colors are also consistent with colors of asteroids. It's rotating. You can measure the rotation period from periodic shifts, changes in the apparent brightness. The rotation period is about 7 hours, making reasonable assumptions about the albedo. The brightness tells you the mean radius. It's about 50 meters. The amplitude of the light curve is somewhere between a factor of 6 and 10. So this is a logarithmic plot of the brightness as a function of time. Here's a factor of 10. You can see there are these huge variations in the brightness. And the reason the observations are somewhat ratty, of course, is that it was going through the system very fast. And although lots of people used their telescopes to look at it, it was a motley selection of observations. Its velocity outside the solar system, if you extrapolate it back outside the solar system, doesn't match the velocity of any nearby star. For example, since the comet cloud is so large, our comet cloud is 10 or 20% of the distance to the nearest star. You could imagine it was just associated with the comet cloud of some other star, but people have tried to match its velocity to all the other stars within 10 parsecs, and there's no match. Okay, so let me talk now about the puzzles that this poses. The first puzzle is the required number density. If you say, okay, we've detected one such object, we know the selection function for the Pan-STARRS survey, you can do a careful calculation and conclude detecting one of them within the statistical errors implies that the density of these things in interstellar space is a little under 0.2 per cubic astronomical unit. If you then make the simple assumption that every star in the solar neighborhood produces these objects at the same rate, every star has to produce about 40 Earth masses in these bodies. Now, for comparison, the entire mass in planetesimals in the solar system used to create all of the planets, plus the Oort cloud, plus everything else, was probably around 50 to 100 Earth masses. Of this in the solar system, at most, maybe half of it was ejected. So we're already getting pretty close to this limit if you take only half of this. On the other hand, we know that only 10% of stars host giant planets that are massive enough to eject them. So it's suddenly getting very hard to produce enough mass in solid bodies to get a reasonable probability of one of them coming through the solar system and getting detected.
Sorry, I think I'm missing a fragment of the logic. The thing we've detected is very much smaller than that, less massive. I mean, so are we worrying about the things that were capable of ejecting it?
Let's say you took all of the solid mass in the planetary system and you chopped it all up into things that were identical to Oumuamua, same size. That gives you the total number of those objects. Let's say you eject half of them, and say that every star does that, then the numbers work out about right. But only 10% of the stars have planets that could eject them. So maybe you can get away with it, but it's not easy.
So how do you compute the probability? Let's say that 10%, let's say that you had 0.02 per AU cubed. What would be the probability of observing such an object?
Basically, you get a bunch of people who work on pan-stars. They know the area that it observes every night. They know the magnitude limit. So then they do a calculation.
I'm asking for the actual number. Let's say that you had only 0.02 per AU cubed. What would be the probability that we see such a thing?
10%.
10%. So it's not like.
No,
Okay.
I agree.
It's not like 5 sigma.
Right. Okay, problem number 2, it gets worse. Problem number 2 is the lack of a coma or a tail. Any icy body is much more visible than a rocky body. I said earlier that you only see comets. You see comets much more easily because they have this big tail. So it's far easier to detect a comet than it is to detect a rocky body. And so you can work out, if you just say the first object that we detected, first interstellar object we detect that is rocky rather than icy, that means there have to be many more rocky bodies than icy ones because they're much harder to detect. And when you do it quantitatively, you find that the fraction of icy bodies in interstellar space compared to rocky ones should be less than 0.1%. On the other hand, rocky bodies are much less likely to be ejected than icy bodies, at least in our solar system, because icy bodies are formed at larger distances. There are more massive planets at larger distances. The escape speed from the planetary system is lower at larger distances. So why doesn't ʻOumuamua show a coma? It's extremely puzzling that it should have, it should be rocky rather than icy. Puzzle number 3 is, as I said, the light curve shows a maximum to minimum range of a factor of at least 6 to 10. If you compare that to known asteroids, this is the amplitude, here are all of the asteroids, here's the spin rate, there's ʻOumuamua. The spin rate is not unreasonable, a period of around 7 or 8 hours, but the amplitude is far larger than the vast majority of asteroids we know of. To get that amplitude, the axis, if you model it as a triaxial ellipsoid, the axis ratio has to be at least 6 to 10, and that's assuming that the spin axis is normal to the line of sight. If the spin axis is along the line of sight, you need a much larger axis ratio. This argument gave rise to this famous picture of what it must look like. Obviously, there's a certain amount of artistic license in there, but the axis ratio is about right. Moreover, if you, because it's so elongated, even though the period is not that different from the periods of some asteroids, because the axis ratio is so big, that angular speed, it's rotating faster than breakup. That is the point mass at the ends of this rotating thing. The centrifugal force would be larger than the gravitational force.
So what's the length of that thing?
About 100 meters.
Okay. So it means it can't be a rubble pile.
Yes. The next puzzle has to do with its velocity. If you extrapolate the orbit back to infinity, this is the velocity in standard galactic coordinates, total of around 30 kilometers a second. In the region of the sun, you can define a local standard of rest, which is the mean velocity of all the stars. In the same coordinates, the best estimate of that looks like this in this coordinate system. Now you can see that in this direction, perpendicular to the galactic plane, the velocity is almost exactly the same as the local standard of rest. in the radial direction towards the galactic center. It's almost exactly the same as the local standard of rest. It's quite different in the azimuthal direction, but the errors in trying to estimate that mean velocity are much larger in the azimuthal direction than they are in the two other directions. And in fact, there have been at least...
In W direction, also the sign is opposite, no?
A typo.
That's a typo.
Okay.
Other than that, it's fine. Okay, so the azimuthal velocity is wrong, but is also very uncertain. Now we know, so why, if it really is so close to the local standard of rest, what we know is that gravitational kicks from giant molecular clouds and spiral arms generally increase the dispersion of a population relative to the local standard of rest with age. If ʻOumuamua is so close to the local standard of rest, it must have been traveling through the interstellar medium along with its host star for a very short time, less than a gigayear or less than about 10% of the age of the solar system. So if that's true, first of all, why didn't we see something earlier for the first object that we got? Maybe something destroys them, but we don't know what that would be. And of course, if it's young, the problem of the mass budget just suddenly got another factor of 10 worse. The next problem is a more recent one. Just this summer, a very careful analysis of the orbit found that the residuals in two coordinates, right ascension and declination, could be reduced by about 30 sigma if you assume that there was an extra non-gravitational acceleration to ʻOumuamua. Normally, the amplitude of the non-gravitational acceleration is about 10 to the minus 3 of the solar acceleration, but it's very significant. Normally, this sort of thing occurs if you have a comet which is outgassing, but again, there's no evidence of any outgassing, and it looks like the object is rocky. Also, unless the object is perfectly symmetric, if it has any asymmetries, that level of non-gravitational acceleration is going to imply an unrealistically fast spin up or spin down, so the rotation period would get much larger, much smaller within a few weeks. So that doesn't seem very likely.
Meaning if the non-gravitational force is coming out from anywhere other than exactly its center of mass,
Yes.
it would tend to torque the
Right.
object. Yeah, I see.
Is the R in that expression the radius to the distance to the sun, or what?
Yeah, distance to the sun. So the form of the non-gravitational acceleration, like gravity, is reasonably well fit by 1 over r squared force. So for instance, one possibility, one thing that behaves that way is radiation pressure. But the radiation pressure on an object of that size is negligible. Okay, so I feel I have to ask the question.
I was hoping that would happen.
Okay, so I've listed a set of 5 puzzles, or 6 puzzles. The required number density, the spaceship does a reasonable job of solving that, because of course if you're sending out a spaceship, you don't send it out in a random direction. You send it into some star that has a reasonable looking chance of habitability. The lack of coma, the fact that it doesn't have it's not made of ice, is of course automatically explained because spaceships are made of metal, they're not made of ice. The problem of shape, you recall, as we all know what spaceships looks like, so that problem is solved.
But what if it was spinning? The shape just comes from the magnitude of the.
Yes.
Right?
Yeah, and it's
so what if
tough
it's
like-
spinning and has windows? So sometimes the sun comes in, sometimes you're seeing the
Reflection off the windows?
Write a nature paper. Okay, it doesn't explain why velocity is close to the local standard of rest. It does a very nice job of explaining the non-gravitational acceleration, because if it's a spaceship, it's hollow. If the non-gravitational acceleration is due to radiation pressure, you can work out what the corresponding density of the object has to be, and it's consistent with a hollow object with a wall thickness of a few centimeters, which is just what you would want for a reasonable spaceship. And it doesn't particularly explain why the colors are similar to some asteroids. So I think the proper way to look at this, these arguments, for instance, the non-gravitational acceleration, is it's a 30 sigma effect. So do you think the prior probability that it's a spaceship is more or less than 30 sigma? And then you will know what the answer is. Okay, let me summarize. There is a simple standard model for the formation of the Oort cloud. It explains most, but not all, of the properties of the observed comet orbits. Properties of Sedna and other members of its population can be explained by the presence of a few Mars to Earth mass bodies and protoplanetary disk. And if that's true, there's a significant probability that one, maybe two of these bodies are still in orbit hundreds of astronomical units from the sun. Oumuamua is very difficult to explain. The good news is that it was discovered not that long into the lifetime of pan-stars, when pan-stars had sufficient capability and software to discover it. That means that this is sort of like the first gravitational wave event. You discover something pretty soon after you start the survey, and in any reasonable model you ought to discover some more events in the near future. So we can look for the discovery of more of them and see how many of these strange features are discovered. And finally, during the question period, I'll just put up a summary of the possible undiscovered planets from XKCD. Okay, thank you.
Do you know whether Oumuamua has had other previous interactions with different stellar systems?
Who knows?
So the Sedna thing, it's because of its size? Is that the issue?
No,
Because it's not that big. I mean,
no, the size is not a problem. The size is big just because it's so far out that you couldn't see it unless it was that big. The problem is that its orbit is isolated from the giant planets.
Yeah.
That means that unless you do something irreversible, it just sits in that orbit for 5 billion years and the orbit doesn't change. And therefore, it's very hard to see how it could have been formed, since the only place we know of to form objects like that is much further in the protoplanetary disk.
Okay, but then you said you might see, you related it to Earth mass and Mars mass bodies.
I was using the Earth and Mars mass bodies only as gravitational perturbers to change the orbit of Sedna. The argument would apply equally to Sedna or to something a tenth of the size. It's just that you don't see objects a tenth the size of Sedna out at those distances.
You probably mentioned, but I missed it. What are the inclination of these Sedna-like bodies?
20, 30 degrees.
Is it consistent with your diffusion type argument?
Yeah. So the diffusion arguments, let's see. So the population that we get from the simulations have inclinations of around 10 to 30 degrees, and that's entirely consistent with the inclinations of the observed population.
So if your rate is right for the ʻOumuamua, or whatever pronounce it, when's the next one?
Well, it's a Poisson process. We roughly know how long the survey has been operating. We have one event. It's a simple exercise in statistics to figure out when the next event should be.
But does the spaceship hypothesis have any implications for the rate?
Well, presumably that depends on whether they're sending a fleet or...
I guess if it comes from the same direction, that's concerning. Is ʻOumuamua, you almost implied that ʻOumuamua is the best measurement of the local standard of rest.
That's correct. I did almost imply it.
That is a very strange argument. It's worth working that out, because if it is,
Well,
maybe we could replace
Right.
it.
So the answer is,
Because the local
of course.
standard, of course, I don't agree that that's the best measurement of the local standard of rest.
of course.
But it's a kind of
So
chimera.
I'm not arguing that it's the best measure, but if we had 24 of them,
Mhm.
and if they all looked the same,
Yeah.
then I might well
Yeah.
argue that it was.
Yeah.
Early on, you showed the imprint of Jupiter that it made on the distribution of perihelions and the comets. What's the minimum mass required for a planet like that to leave such a sharp imprint on the comet population?
All that really matters is not that it's so massive, but that it's the most massive one.
I see. Okay.
So if Jupiter were the only planet, you would get an imprint like that, pretty much whatever mass it had.
Okay.
If we didn't have a Jupiter, but had Saturn, then Saturn won't do it.
Yeah.
So there's so many close-in giant planets. What would what kind of Oort clouds would those systems have?
That's a very good question. I've thought about that a little. Nobody's really tried to do this in any detail. I mean, if you really want it to be comets, the answer is nothing, because the comets would evaporate here. I've already got close enough to the giant planets. But I think the proper conclusion to draw is that you really don't want to go around assuming that every star has a cloud just like ours. There's a huge, the properties of the cloud, the mass, the size, are really sensitively dependent on the geometry and the masses of the planets. So there could be a huge variety.
But that does undermine your claim that ʻOumuamua is a spaceship.
I didn't claim it.
but the one of the puzzles, or some of the puzzles, are related to the fact that our Oort cloud, but that it's unlikely that it would be produced by our Oort cloud. But if there's a lot of stars that have much more compact planetary systems, it might be that all the volatile things.
Well, but the only argument I made was that was saying that you have roughly the same amount of solid material in the protoplanetary disk, and okay, forget about somehow eject. It's hard to believe you can eject more than half of it, because you have to put some of it into the giant planets.
Yeah.
So eject half of it. That's the most you can do, and even then, it's not enough.
Yeah, but there might be enormous. We might be somewhere in a kind of power law distribution of stars, and it might be that most of the interstellar material is actually donated by a small fraction of the stars.
I agree.
Did you go back to that plot which 3 or 4 slides ago showing the orbits, and you showed the orbit of ʻOumuamua? And then,
This one?
yeah. So the one showing the path, is that, should we take that as an artist's conception, or is that, I mean, because then it seems like it really does encourage the spaceship argument, because why would it be coming from some random direction and pointing right to us?
Because if it wasn't, we wouldn't have seen it.
So presumably there's a huge rain of such objects. This picture must be that there's a huge rain of such objects, and we just happen to catch this one.
Right. I mean,
Right? That's
right. So the argument
Because
was.
you didn't put that part of it into your discussion.
Yeah,
Did you?
so there's this estimate that the density that you need is about 0.2 per cubic astronomical unit. So what that says is that even within the planetary system,
There's tons.
there are thousands of ʻOumuamuas right this instant passing through. It's just that this one happened to be the one that came close enough after Pan-STARRS was turned on that we saw it. But of course, it is true that the requirements on the mass would be drastically reduced if somebody was aiming on that.
Yeah, exactly.
Can we go back to, go ahead.
Sorry, just following up on it being a total spaceship. What's the constraint on the size, because it looks like a point object?
That's much worse than a constraint from the flux.
Yeah, but they painted it.
I mean, they painted it black,
Yeah.
or it's a stealth.
Then it could be huge. Then it would be immense, right?
Yeah,
That
but
would be
so
natural.
the constraint on the size is, I forget the exact number, but it's much bigger than.
It's more or less assuming, right now it's more or less assuming that it's a piece of iron, right? Isn't that roughly
the standard estimates are for a density of 3, which is lower than iron.
So you presented sort of 3 different hypotheses for what a planet 9 might be. Are any of those, do any of those exclude the other ones, or could we have a 9, 10, and 11?
Absolutely. None of them are excluded. You could easily have multiple. You could have half a dozen in the Oort cloud. Batiguin and Brown would like to have one of 1,000 astronomical units. So sure.
Maybe we can continue the grilling at the reception.
Good, yeah.